Welcome to the presentation, Introduction to Sensors, produced by the Southwest Center for Microsystems Education. In this presentation, we will be answering the question, what are sensors? We will also be discussing several types of sensors, both in the macro and the micro scales. A sensor is a device that receives and responds to a signal. This signal, which is the sensor's input, must be produced by some type of energy such as heat, light, motion, or a chemical reaction. Once a sensor detects an input, it converts it into an analog or digital representation. Based on this explanation of the sensor, you should see that sensors are used in all aspects of life to detect and or measure many different conditions. What are some sensors that you are familiar with or that you use daily? How about thermostats, tilt sensors in your phones and cameras, and even cruise control? All of these are sensors. Human beings are equipped with 5 different sensors. Eyes detect light energy, ears detect acoustic energy, a tongue and a nose detect certain chemicals, and skin detects pressures and temperatures. The eyes, ear, tongue, nose, and skin receive these signals, then send messages to the brain, which outputs a response. For example, when you touch a hot plate, it is your brain that tells you that it is hot, not your skin. This unit describes the basic concepts of sensors and introduces several types in both the macro and micro scales. Sensors detect the presence of energies as well as changes in or the transfer of energies. Sensors detect by receiving a signal from a device such as the transducer, then responding to that signal by converting it into an output that can easily be read and understood, such as an analog or digital readout. In many sensors, the sensor compares the input and output signals, quantifies any change, and responds with an appropriate output. Let's take a look at an oven temperature sensor. This diagram shows how a sensor works. The oven is initially programmed with a set point, in this case 350 degrees Fahrenheit, and this turns on the heating element. As the oven heats, the oven's thermocouple converts the temperature of the oven to a voltage. This voltage is read by the sensor's electronics. The sensor compares the set point to the thermocouple output. If the thermocouple output is less than the set point, the sensor keeps the heating elements on and displays the actual temperature. Once the set point and the actual temperature, as sensed by the thermocouple, match, then the heating element is turned off. Just like there are different types of transducers, there are many different types of sensors. Thermosensors are devices that measure hot and cold. Thermal sensors use some type of transducer that converts temperature or heat to another form of energy. For example, a thermometer, like the one you use to take your body temperature, measures absolute temperatures, which are temperatures relative to absolute zero. The thermometer in the picture is an infrared thermometer that can sense body temperature without contact with the body. These thermometers work using an occurrence called black body radiation. The amount of black body radiation that a person emits is solely dependent upon the body's temperature. The higher the temperature, the more black body radiation is emitted. An infrared thermometer measures the amount of black body radiation, converts it to temperature, and provides a readout. Other thermal sensors include thermocouple gauges, which use thermocouples to measure temperatures, and RTDs, are resistant temperature detectors. RTDs are a coiled wire that exhibits a change in resistance when the temperature of the wire changes. RTD sensors monitor the resistance change and outputs a reading of the effective temperature. Another type of sensor is the mechanical sensor. Mechanical sensors use movement of some type to sense a specific parameter such as pressure, the flow rate of fluid, or acceleration. An example is the aneroid barometer shown in the graphics. An aneroid barometer senses change in atmospheric pressure by the expansion and compression of a thin disc-shaped capsule, usually metallic and partially evacuated of gas. An external spring is connected to the capsule, and a needle is mechanically linked to the spring. As the pressure on the outside of the capsule increases, the capsule compresses, causing the spring to move the needle, indicating an increase in barometric pressure. As the pressure drops, the capsule expands and the spring moves in the opposite direction, moving the needle to show a decrease in barometric pressure. Other types of mechanical sensors include the pressure sensor, which measures pressure, barometers, which measure atmospheric pressure, and altimeters, which measure the altitude of an object above a fixed level. We also have liquid flow sensors, which measure flow rates of liquid, gas flow sensors, which measure velocity, direction, and the flow rate of a gas, and accelerometers, which measure acceleration and deceleration. Electrical sensors are sensors that measure changes in resistance, current, voltage, or electrical energy. Examples of electrical sensors are the ohm meters, which measure resistance, voltmeters, which measure voltage, galvanometers and ammeters, which measure current, and watt-hour meters, which measure the amount of electrical energy supplied to and used by a residence or business. The images show a galvanometer, which is a special type of ammeter. A galvanometer senses and measures the amount of current flowing through a wire. In a galvanometer, current flows through a coil, the red wire in the leftmost image. This current creates a magnetic field around the coil. The coil sits inside another magnetic field, which is created by permanent magnets that surround the coil. The interaction of these two magnetic fields causes the coil to pivot around its central axis. The amount and direction of the pivot move the needle at the readout, as seen in the right image, left or right, indicating the level of current and its polarity, negative or positive, respectively. This device uses two energy conversions to sense and quantify an electric current, electrical to magnetic and magnetic to mechanical rotation. Chemical sensors detect the presence of certain chemicals or classes of chemicals and quantify the amount and/or type of chemical detected. For example, an oxygen sensor measures the percent of oxygen in a gas or liquid being analyzed. A carbon dioxide sensor detects the presence of CO2 or carbon dioxide. There are chemical sensors that detect a specific gas, such as CO2, arsenic, or ammonia. However, microtechnology has enabled the ability to fabricate micro-sized sensors that can detect several different gases simultaneously. Chemical sensing has really taken off with microtechnology. Just like the macro-sized components, MEMS chemical sensors can detect a wide variety of different gases, but they can detect several at a time, and because of their size, they can go places that macro sensors can't really go. MEMS sensors can also be incorporated into objects such as military clothing for continuous sensing of a gas or selection of gases. MEMS chemical sensors have numerous medical, industrial, and commercial applications, such as biohazard detection, quality control in food processing, and medical diagnostics. Such devices are sometimes referred to as an e-nose or electronic nose. Optical sensors detect light of a specific wavelength or light within a range of wavelengths. The manner in which light is detected depends upon the type of optical sensor. For example, the photocells seen in the pictures use photovoltaics to convert light energy directly into electricity. The photocells on the International Space Station are double-sided, maximizing the amount of light detected. The electricity generated by these cells supplies the electricity for all operations aboard the station. Photodetectors, which we are all familiar with in one way or another, range from simple resistive photocells to photodiodes and transistors. Proximity detectors use light to sense when objects are nearby. They contain an LED source and a detector to measure reflected light. Such devices are small enough to be used in small electronic appliances, computers, and cell phones. They are used for determining the alignment of paper in a copier, if a laptop case is open or closed, or if a hand is in the wrong place in a piece of equipment. Infrared sensors are used in situations where visible light would be inconvenient or counterproductive. They can be used to tell if someone's in the room by the amount of heat given off by the person's body. As we saw previously, infrared sensors are being used to measure body temperature by measuring the amount of black body radiation. Other types of sensors include acoustic sensors, such as the acoustic wave sensor, which measures the wave velocity in an environment to detect the presence of a chemical species, or in a seismometer, which measures seismic waves. There are also motion sensors, such as accelerometers and gyroscopes, which detect motion, acceleration, rotation, and vibration. Speedometers, which measure speed, Geiger counters, which detect atomic radiation, and biological sensors, which can detect and sense and measure specific biological molecules in the human body, are other types of sensors. Transducers and sensors can be found in both the macro and micro scales. For most macro sensors, there is an equivalent microsensor that can perform the same function or functions more efficiently and in many cases for lower production cost. The images seen here show a macro-sized pressure sensor on the left and its equivalent micro-sized sensor on the right. The pressure sensor on the left is a capacitance manometer. Underneath the electronics board that you can see is a diaphragm and a reference chamber that are used to measure changes in pressure. The right image shows the micro-sized diaphragm and the electronic sensing circuit. Both components perform the same function. However, their size difference is dramatic. You can see this in the left image. The green circle is around a MEMS pressure sensor, which you can see is extremely small in comparison. Other such comparisons can be found with pumps, inertial sensors, chemical sensors, and photosensors, and many, many more. As we've said many times before, a transducer is a device which converts one form of energy to another. When the output of the transducer is quantified and converted into a readable format, the transducer is called a sensor. Therefore, a sensor is a device that receives and responds to a signal. The signal usually comes from a transducer as some type of energy such as heat, light, motion, or chemical. Thank you for using this learning module from the Southwest Center for Microsystems Education.